Control of signaling by phosphorylation and dephosphorylation. Regulation by insulin response. Introduction. Phosphorylation and dephosphorylation are fundamental post-translational modifications that act as molecular switches, regulating a vast array of cellular processes. Insulin, a key hormone in glucose metabolism, exerts its effects largely through these mechanisms. This intricate interplay between insulin, phosphorylation, and dephosphorylation orchestrates a complex signaling network with profound implications for metabolic homeostasis. The role of phosphorylation and dephosphorylation. Phosphorylation. The addition of a phosphate group to a protein, typically on serine, threonine, or tyrosine residues, catalyzed by kinases. This modification alters protein conformation, activity, and interactions. Dephosphorylation. The removal of a phosphate group, catalyzed by phosphatases, reversing the effects of phosphorylation. Insulin signaling and phosphorylation. Upon binding to its receptor, insulin initiates a cascade of phosphorylation events. Insulin receptor tyrosine kinase, IRTK, activation. Insulin binding induces autophosphorylation of the insulin receptor, activating its tyrosine kinase domain. Insulin receptor substrate, IRS, phosphorylation. Activated IRTK phosphorylates IRS proteins on multiple tyrosine residues, serving as docking sites for signaling molecules. Activation of downstream kinases. Phosphorylated IRS proteins recruit and activate signaling molecules such as PI3K, which generates phosphatidylinosyl 3,4,5 trisphosphate, PIP3. PIP3 activates ACT, protein kinase B, through phosphorylation. Cellular responses. ACT, as a central player, phosphorylates various substrates, leading to glucose uptake, glycogen synthesis, protein synthesis, and lipid synthesis. Regulation by dephosphorylation. Dephosphorylation is equally crucial for terminating insulin signaling and maintaining cellular homeostasis. Protein tyrosine phosphatases, PTPs. These enzymes dephosphorylate insulin receptor and IRS proteins, attenuating the signaling cascade. Protein serine threonine phosphatases, PSPs. These phosphatases act on downstream targets of ACT, such as glycogen synthase kinase 3, GSK3, to modulate their activity. Negative feedback loops. Dephosphorylation often participates in negative feedback loops to prevent excessive signaling and maintain cellular balance. Insulin resistance and impaired phosphorylation. Dephosphorylation. Insulin resistance, a hallmark of type 2 diabetes, is characterized by a reduced response to insulin. This condition is often associated with decreased tyrosine phosphorylation of the insulin receptor and IRS proteins, increased serine phosphorylation of IRS proteins, interfering with insulin signaling, impaired ACT activation due to reduced phosphorylation, altered phosphatase activity, contributing to the imbalance in phosphorylation, dephosphorylation. Therapeutic implications. Understanding the role of phosphorylation and dephosphorylation in insulin signaling provides valuable insights for developing therapeutic strategies for diabetes and metabolic disorders. Targeting kinases. Developing inhibitors of specific kinases involved in insulin resistance could be beneficial. Targeting phosphatases, activating phosphatases, or inhibiting phosphatase inhibitors might enhance insulin sensitivity. Modulating phosphorylation sites. Identifying specific phosphorylation sites, critical for insulin action, can guide the development of targeted therapies. Conclusion. Phosphorylation and dephosphorylation are essential for the regulation of insulin signaling and glucose metabolism. The intricate balance between these processes is crucial for maintaining metabolic homeostasis. Dysregulation of phosphorylation, Dephosphorylation contributes to insulin resistance and type 2 diabetes. Further research into these mechanisms holds promise for developing effective therapeutic interventions.